We have one last topic to cover in Chapter 4 at the end of Section 3, and that is least common multiples. One of my favorite problems to illustrate this idea is thinking about hosting a party where you want to serve hot dogs. When you go to the store, maybe you notice that the actual hot dogs themselves are sold in packs of 10, but the buns are sold in packs of 8, which is a little bit ridiculous. It's a huge scam just to get us to buy more. But we're smart. We can figure out how many packs of hot dogs to buy and how many packs of buns to buy to make sure that every hot dog has a bun. And the way that we're going to answer this is by looking at the LCM of 10. 10 because 10 hot dogs come in a package, and 8. 8 because 8 buns come in a package. Now, if we just looked at any common multiple, we could answer this question quickly. We could easily say buy 8 packs of dogs, buy 10 packs of buns, 8 packs of dogs with 10 dogs in each pack, that's a total of 80. 10 packs of buns with 8 buns in each pack, that's a total of 80. So if we did it this way, we could have 80 hot dogs with buns, problem solved. But maybe you don't want to buy 80 hot dogs. I mean, maybe you do, but let's assume that you're looking for the smallest combination of hot dogs and buns we can get away with. That's why we need the least common multiple. If we list out our multiples of 10, we get 10, 20, 30, 40, 50, 60, 70, 80, 90, etc. We can also list out our multiples of 8. That's going to look like 8, 16, 24, 32, 40, 48, 56, 64, and 72. We could keep going, but why not? 80, 88. That's good enough. If we look at our list of multiples, there are a couple of numbers that show up in both lists. For example, I see 40, and I also see 80. So 80 is a common multiple, but it's not the smallest. 40 is a common multiple, and it is the smallest. So this is the answer that we might like best because we only have to buy 40 hot dogs and buns for our party rather than 80. So this is an application of least common multiples. There's a few different ways that we can illustrate how to find least common multiples. One of them is with a number line. This is really similar to that process of finding common divisors using the blocks, but here we're lining up arrows, and we're using arrows of length 4 and length 3 because this problem's asking for the LCM of 3 and 4. And we just stack up the arrows starting at 0 and continuing to stack them up until they line up at a common value. So a least common multiple of 3 and 4 would be 12. We can do the same thing with the rods. So we can look at common multiples of 3 and 4, waiting until we find where they match up at a common value. And the only, downside to doing the rods instead of the number line is we can't see what that value is. We'd have to count it. So 3, 6, 9, 12 if we counted by 3s, or 4, 8, 12 if we counted by 4s. One way to calculate our least common multiple using a Venn diagram is to look at the intersection of sets. So I have all of my multiples of 3. I'm going to put those in the red circle. And multiples of 4 I'll put in the blue circle. And any numbers that show up in both lists, I need to make sure to put those in the intersection. So 12 shows up in both lists, so does 24. And then for the rest of the multiples of 3, I can sort them over here. I have 3, 6, 9, 15, 18, 21. And the other multiples of 4, I'll put 4, 8, 16, 20. Once we have our multiples organized like this, we can look at the intersection of the two sets, which is this intersection here. And we're looking for the least common multiple, so we'll pick the smallest number in that intersection. We can try it again with the numbers 8 and 12. So looking through our list of multiples here, I see 24 shows up in both lists, 48 shows up in both lists, 72 shows up in both lists, 96 shows up in both lists. So we'll sort them, putting the numbers that show up in both lists in the intersection, and then organizing the rest where they belong. So I'll put the multiples of 8 in the red circle, multiples of 12 in the blue. Oops, I almost wrote, well, I did write 24 over here, but it doesn't belong there because it's already in the intersection. So I'll skip 24, put 32, 40, 56, 80, 88, 104. And then for the blue, I have 12, skip 24, it's already in the intersection, 36, 60, 72. Oh, nope, 72 is already in the intersection as well. So I skip that one, put 84, 108. Now you're probably thinking, if you already have these numbers in a list like this, why would you bother putting them in the Venn diagram layout? And honestly, it's just a way to help our brains visually grasp why we're picking the numbers we're picking. So in a list like this, it's possible that you might accidentally look over a number that's common multiple. When you put them in a Venn diagram like this, it's a little easier to see where the overlap is. Oh, we didn't really finish that problem, did we? We're looking for the least common multiple, so we look in the intersection and pick the smallest number. So our least common multiple of 8 and 12 is equal to 24. Now here's a similar situation. We're looking at least common multiple. We're going to use our Venn diagram. However, we're not going to just list out the multiples. Instead, we're going to look at our prime factors, and we're going to use those prime factors to help us create the least common multiple. So we're looking for the least common multiple of 2,520 and 10,530. The numbers are already factored for us, so that's great. In order to use this Venn diagram to find the least common multiple using prime factors, we're going to look at which factors are in common. They both have a 2, they both have some 3s, they both have a 5. 2,520 has a 7, 10,530 has a 13. So we know those are definitely different factors. Let's go ahead and label our circles. The red circle will be the factors of 2,520. The blue circle will be the factors of 10,530. Since I know that 7 is a factor that belongs to the red circle and not the blue, I'll put it over here. And 13 will belong to the blue circle and not the red, so I'll make sure that that does not fall into the overlap either. I do know that both numbers have some 2's. 2,520 has 3 factors of 2, 2 to the third power, but 10,530 only has 1. So if we look at what they have in common, they each have 1, but then 2,520 has a couple more. So I'll place the one that they have in common in the overlap, and then I will put 2 squared in the red portion because 2,520 needs 3 factors of 2, and if we look at our red circle, we have 3 factors of 2. Same thing for the factors of 3. I noticed that both numbers have multiple factors of 3. 2,520 has 2 of them, 10,530 has 4. So in common, they both have 2, but 10,530 has 2 extra. So I'm going to put a 3 squared in this blue overlap. Sorry, not overlap, in the blue overhang. And if we look at the blue circle, in total, there are 4 factors of 3, just like we need for 10,530. Next, we see that each number has a factor of 5, and that's all of the factors. What I really like about this prime factorization method using the Venn diagram is that I can look at everything in the red circle and I'll see every factor that I need to make the full number. So I have 3 factors of 2, 2 factors of 3, 1 5, and 1 7. Same thing for the blue circle. If I look at just the blue circle, including that overlap, I can count that I have 1 factor of 2, 4 factors of 3, 1 5, and 1 13. Now, in order to create the least common multiple, I'm going to use every single number that appears in the Venn diagram. So I'm going to have, from just the red portion, 2 factors of 2 and the 7. From the intersection, that overlap, I'll have another 2. I'll have 2 factors of 3 and a 5. And then from the blue part, I have a 13 and another 2 factors of 3. When I multiply all of these together, I get the LCM. And it's easier to group common factors. So I've got 3 factors of 2. I have 4 factors of 3, 1 factor of 5, 1 factor of 7, 1 factor of 13. Let's go ahead and type those into our calculators. And my calculator is telling me that we have 294,840. That 4 looks strange. Let's fix it. A little better. That's our least common multiple. Now, if we look at the factors here, they look a lot like the factors here, where we've picked the highest exponent on each of the common prime factors. Between the factors 2, we have 2 to the first power, or 2 cubed. We used 2 cubed. For the powers of 3, we have 3 squared, or 3 to the fourth. 4 was the bigger power, so we used 3 to the fourth. There was exactly 1 factor of 5, so in this case, it doesn't really look like we picked the bigger one because they were equal, but we did use 5 to the first power in our the least common multiple calculation. We also had 1 7. Now this is not a common number, but in order to use it, in order to calculate the least common multiple, we need to make sure that all of the factors of each number appear. So we did have to include the factor 7 in our calculation. And then of course the same thing with the 13. So if you want to use prime factorization, you could just list out the prime factors, look at the common prime factors, pick the factor with the higher exponent, or you could write it out in a Venn diagram and use all of the factors, making sure that we're not double counting anything. What kind of thing could you possibly double count? Well, let's look at the factors of 3, for example. We have 3 2 factors of 3 in our small number, 4 factors of 3 in our large number, it would be a mistake to use all 6 factors of 3 because that's more than what we need. We just need 4 factors in order to make the number that has more factors of 3. So we just pick the highest power on the common factors. There is this cool relationship between our greatest common divisor, our least common multiple, and the product between the numbers for each calculation. So the GCD of a number A and B times the least common multiple of a number A and B, that's equal to the actual product of A times B. We can use this equation to help us find a least common multiple between two large numbers. That's because writing out a list of all the multiples of 731 or all the multiples of 952, that would be pretty time consuming. The numbers would get rapidly fast. Also, these numbers are kind of big as far as prime factoring. We don't probably want to prime factor them all the way down. So instead, we can use this relationship that says take the GCD of the two numbers, multiply it to the LCM, and that's equal to the product A times B. Let's work through an example. First, we need to find the GCD. So if we're looking at 731 and 952, we want to find the GCD between those numbers. We have a few options. We can do set intersection, prime factorization, Euclidean algorithm. Use whichever technique you'd like to. So whatever technique you choose, you'll find that the GCD of 731 and 952, it's equal to 17. So no matter which method you use, you'll find the GCD is 17. So pick whichever method you like. Next, we're going to take that 17, plug it into the GCD portion of the equation. So if we have GCD times LCM is equal to A times B, we can replace the GCD with 17. We're going to leave the LCM there because that's the thing we're looking for. And then we can replace A and B with the numbers that we used. So 731 times 952. Since the LCM is the only thing in the equation that we don't have a value for, we can isolate it. Right now it's being multiplied by 17, so we'll divide both sides of the equation by 17, leaving us with the LCM is equal to 731 times 952 over 17. Now, because 17 is a common divisor, I know 17 will divide each of these numbers. 17 will divide 731. In fact, it goes into it 43 times. Also, 17 goes into 952 56 times. Now, I don't like multiplying big numbers, so what I'm going to do is divide the larger of the two numbers by 17, reducing that to a 56 and the 17 to a 1, so that we only multiply 731 times 56. To get the LCM of 40,936. So this is just another way to find the least common multiple. If you already happen to know the greatest common divisor, this is absolutely the best way to do it. Otherwise, sometimes this first step, finding the GCD, it almost makes this not an efficient way to calculate the LCM, but just another way to do the same problem. All right, and that's it for chapter 4. So The quiz was posted today. Make sure that you get that submitted to me before tomorrow at 11:30 a.m. So originally it was due at midnight, but because of some technical issues, I didn't get it up until 11:30 a.m. today. So I'm giving a full 24 hours to complete it, upload it. Remember, this is your own work. If you have any questions about the quiz, please direct them at me, nobody else. All right, guys, have a great day.